Good morning, everyone. I'm Sam Weintraub alongside Ashwin Kishan and Connor Sandell. We're members of Team Aerate from the Mechanical Engineering Department, and we are designing a more efficient air conditioning unit that we believe is the future of cooling. The problem that we are working to address is called the Global Cooling Challenge, which is comprised of three key issues. Firstly, increased cooling demand poses a massive threat to the environment and energy systems across the world. Secondly, billions of people are becoming increasingly exposed to dangerous heat conditions. And finally, current initiatives and technology are simply not enough to offset this massive threat. Looking more specifically at the factors contributing to the increase in cooling demand, it can be seen that global temperatures across the world are rising, income is growing, urban populations are growing, populations in general are growing, and simply cooling requires a massive amount of energy. What this means is if no action is taken by 2050, 3.3 billion new air conditioning units will produce an estimated 132 gigatons of CO2 emissions, resulting in a 3x increase in energy demand for cooling. To put this into perspective, this is the equivalent of adding 2 European Unions worth of energy consumption just to meet the increase in cooling demand. This increase in cooling demand is happening in several countries, but the majority of the growth is happening in India, which will see the introduction of 1 billion new air conditioners by 2050. Due to the massive growth potential, Aerate has decided to focus their efforts on this market. Looking more specifically at the Indian market opportunity, currently only 7% of Indians own an air conditioner, but the ownership rate is rising annually. Additionally, 55 million Indians are entering the middle class each year, of which an air conditioner is a key quality of life purchase. And finally, the Indian government is beginning to incentivize the transition towards energy efficient cooling through bulk purchasing agreements and competitions such as the Global Cooling Prize. What this all means is that in order to address the threat posed by the Global Cooling Challenge and reduce our energy consumption relative to today, a 5x increase in air conditioning efficiency is needed. The Global Cooling Prize is a competition sponsored by the Indian government and Richard Branson to promote the development of energy-efficient cooling technologies, and they have outlined few key criteria in order to make this possible. Performance, affordability, target output, and climate impact are all key considerations when developing a new air conditioning system. Looking more specifically at the performance criterion, coefficient of performance, also known as COP, is a key metric used to evaluate the efficiency of an air conditioner. In order to address the global cooling challenge, we will need to achieve coefficients of performance greater than 5 compared to the current baseline of conventional air conditioners of approximately 1.06. Now I'm going to hand it over to Ashwin, who's going to tell you a little bit more about how we're able to achieve this performance.
Thank you, Sam. Evaporative cooling has been used around the world for thousands of years. It's a very simple and efficient technology. You evaporate a small amount of water into dry air, and this cools it down. Despite its efficiency, this process has an issue. It only works with dry air, which is no good for humid environments like India. Aerate introduces a novel membrane dehumidifier in front of our evaporative cooler. It's able to dehumidify air more efficiently than anything that's available on the market today, and thus we can cool anywhere. This is a system that we have a patent application pending on. So our real system actually looks pretty similar to what we have on the block diagram. So you have a dehumidification chamber linked directly to our evaporative cooler, and this whole process is run by a vacuum pump. So we spent most of our engineering effort on the dehumidification chamber. So basically you take in hot and humid outside air and it passes across a membrane. This membrane is extremely permeable to water and selective against air. And the process is being driven by a vacuum pump that is literally sucking the water out of the air. To mechanically assist this process, we introduce a vacuum sweep gas. It's a small amount of outside air that is flowed into the vacuum to push the water out once it crosses the membrane. So this process is well described by the solid diffusion separation model of membrane transport. So the flux of water across the membrane is proportional to a permeability coefficient and the difference in partial pressure across the membrane. So we took this equation and applied it in a few different lights. So from a thermodynamics lens, we characterized the vacuum work and potential efficiency gains of our system. And from a fluid dynamics perspective, we characterized the sweep gas requirements and the residence time within the system. And from a membrane transport perspective, we characterized the actual selectivity and permeability of our real membranes. So we took those two characterizations and we used them to try to get closer and closer to the theoretical efficiencies of our thermodynamics calculation. So based on this analysis, we identified a few trade-offs within our system, including the dehumidification versus the flow rate and the vacuum work versus the sweep rate. An example of one of these trade-offs can be seen above. So the percentage vacuum on the x-axis goes from 0 to 100%, 100% being full vacuum. On the right-hand side, you have the amount of humidity being removed, or on the left-hand side, excuse me. It's the amount of humidity being removed in blue, and this increases linearly after a minimum amount of 95% vacuum. However, the amount of work required to achieve that dehumidification on the right-hand side increases on an inverse log scale. So as you get more and more dehumidification, you're paying more and more work to achieve it, which is a trade-off for our system. So we took our analysis and we applied it to identifying the correct membrane material for us. So we wanted high vapor permeability and high selectivity. That corresponds to the top right corner of the chart. So we identified 3 membrane materials, Nafion, Pebax, and Speak, and we tested 2 of them which are commercially available and identified Nafion as the ideal material for us because of extremely high selectivity. Based on these designs, we came to the final membrane dehumidification chamber, and I'm going to talk about 4 different aspects of it today. So our system has a modular design. There are 5 identical stacked modules. Each module consists of a feed chamber and a vacuum chamber separated by a membrane. We use this design to ease design for manufacturability. Our system has 95 total parts, but only 11 unique ones between them, a very low number. Diving deeper into a single module, we have a membrane support, which is used to evenly support the membrane without pinching or puncturing. This required many iterations before we came to the Aerate permahex, which is a hex cell structure with openings in between to allow sweep gas and humidity to pass through the membrane out through the vacuum pump. This is the membrane layer under vacuum, and you can see the hex structure actually at work. So within our system, as I mentioned before, sweep gas is extremely important. So the way we're able to incorporate it is we use a manifold that introduces sweep gas into all the layers in parallel, and then it's passed across to the vacuum pump. This is important to shear the water off the membrane because our system has an interesting membrane that requires this component. It's extremely novel. So going back to the feed side, it's important to maximize the residence time on the feed side and to maximize the flow rate through the system. And these are actually in contradiction. So the way we were able to optimize this was by creating an S-shaped flow path through the system where each ounce of air is passed across multiple membrane layers. Thank you. I'm going to hand it back to Connor to talk about the rest of our system.
Thanks, Ashwin. So of course we didn't get to this final design that you see in front of you overnight. It's actually the result of multiple iterations to characterize different items of our system. So we started out with an extremely small prototype designed to characterize our membrane performance under vacuum and really understand what's happening with the membrane separation process that Ashwin described. Then we moved to a system that was about 20 times bigger in order to understand if our process would scale and test our manufacturing methods. Finally, we moved on to the prototype you see in front of you, which was another 5 times bigger than that system and is ultimately about 2/3 the size of our target prototype. Now I'm going to spend a little bit of time talking about the performance of our system. Here you see a characteristic example of our system at work. Here we have air entering from our environmental chamber at 75 degrees Fahrenheit and 65% humidity. After the air exits the dehumidification chamber that Ashwin described, that drops down to 45% relative humidity, allowing us to cool it in the evaporative cooler all the way down to a chilly 58 degrees Fahrenheit. Overall, we see a move from a heat index of 24 all the way down to a heat index of 14 at an extremely efficient COP of 6.2, substantially higher than the baseline of 1.06 and our target of 5.1. But when we extrapolate these results to a full year of cooling demand, we see an even brighter picture. What you see here is a full year of cooling demand in our target market in New Delhi, India. Essentially, because of our system's unique ability to decouple the dehumidification and cooling performance, when it's extremely hot but not very humid outside, we can take advantage of the fact that we only run our evaporative cooler, achieving COPs of up to 100. That happens about 20% of the year. When you take this into account, over the course of a full year, we expect an average annual operational COP of up to 20, almost 20 times higher than a baseline conventional air conditioner. This also leads to substantial cost savings for users of Aerate, as the unit simply uses less power. Over our forecasted 10-year lifespan of an Aerate air conditioner, an average user of Aerate can expect to save up to $1,000 in power costs from their unit relative to a conventional air conditioner, which is also a massive value proposition for the users. Now, I've talked a lot about the great parts of Aerate, but we also have work cut out for us moving forward. There's two big things we want to focus on. So first of all, we want to boost the flow rate through our system, essentially allowing us to deliver more cooling performance, cool bigger spaces. But the second thing we want to do is decrease our sweep gas residence time. You could basically think of this as increasing the effectiveness of our sweep gas, that gas that's moving the water out of the system. By decreasing the time that any given molecule of sweep gas is spending in the system, we can basically more efficiently carry that water vapor out of our system, increasing the efficiency of our dehumidifier and efficiency of the system as a whole. We believe that these changes will take us from our current operating regime of around a COP of 3 to 6 to an operating regime around 6 to 8, so that in any conditions, we're exceeding our target COP of 5.1 when the full system is running, which will further boost the 20x gains that we're seeing. So, we believe that the prototype in front of you, with small changes, meets all the criteria that we laid out for you at the beginning of this presentation. We'd specifically like to highlight meeting our performance criteria that Sam called out earlier in the presentation. Now, we've spent a ton of time on this, and we're happy to say that Aerate is the world's first membrane air conditioner that is designed to cool a full house or apartment. As a result, we strongly believe that this air conditioner best meets the needs of the Indian market on the basis of cost, cooling performance, design for humidity, and climate impact. Though we've been spending a ton of time on this on the past semester, we're excited to continue working on it and give you a little bit of a sneak preview of what we're working towards. As we work from prototype to product, we're really excited to iron out all the kinks and keep going on this project. We've already filed our provisional patent application, so we're excited to get started and work towards this. I'd like to thank all of our advisors, TAs, and sponsors who have made this project possible. And now, on behalf of all of my teammates, I'd love to answer any questions that you might have about Aerate. Thank you. Yeah, definitely. So one of the great things about this is we are pulling water out, and the addition of a simple vacuum condenser, which is an existing problem, will allow us, or product will allow us to condense this water, and it could be filtered, it could be used to drink, it could also be used directly in the evaporative cooler to further boost the efficiency of the system.
Yes.
What about particulates in the air? How do they impact the membrane?
Click on filtering and lifespan, please. Yeah, so it's definitely a concern for both our system and for indoor air quality. We plan to introduce a HEPA filter in front of the system. This is important because it filters out PM 2.5, which is the predominant chemical particulate in the air, and so it improves indoor air quality, which is something that our customers are really looking for in any air conditioner they're using, and it promotes the lifespan of the membranes, which are designed to be pretty corrosion resistant anyways, but just protects them from that.
Thanks for the presentation. Would you mind going back to the slide where you had the
The example?
Yes.
I don't have listed, but the final so in the end, relative humidity increases to say
Yeah.
So when you use this AC humidity,
So in this iteration, we're using a direct evaporative cooler rather than an indirect evaporative cooler. So the difference is basically that the cooled air coming out of that evaporative cooler in this iteration goes directly to the room. In the next version, we're planning on using this indirect evaporative cooler, which basically instead uses a heat exchanger with room air and exhausts the more humid air. So because the bulk of our focus in this version was on the dehumidifier, we had to take some, compromises in other areas. But we do expect moving forward, we won't have that problem, and we'll actually be able to independently control temperature and humidity of the room by mixing essentially room air with this outgoing air. And over time, what that means is that the humidity of the room will actually decrease, further boosting the efficiency of our system over time. Yeah, so that's including a 70% margin. So our expected COGS is about 30% of that, or $320.
Yeah, I was wondering, what kind of pressure do you have to generate to pull this water through? What kind of maintenance does the user have to do on vacuum?
So because we introduced a sweep gas, the pressure requirement's actually relatively low, and that has to do with you can generate a partial pressure difference doing a couple of different methodologies. In terms of generic maintenance, the most likely thing is going to be replacing the HEPA filter every 2 to 3 years, which is in line with most air conditioners. We don't anticipate needing any maintenance on the vacuum pump, and the membranes have a 10-year lifespan.
So let's have it done. Thank you very much.
Thank you.
Thank you.